In this lesson, we're going to introduce the concept of a second derivative. Okay, so for starters, let me just tell you what a second derivative is. It's really just the derivative of a derivative. Now, before I tell you why you would ever want to find the derivative of something you've already differentiated, let me start by showing you a few notations for it first. Now, we already know that we can write the derivative of y equals f of x as dy on dx. And now if we want to just differentiate this again, we can just apply d on dx directly to this derivative. So as you can see here, we start with some function y, we differentiate it once, and then we differentiate it again. Now whilst this is a completely legitimate way to write the second derivative, we actually have another way that we can write it that's a little bit more succinct. I use this arrow to just mean that this is the exact same thing as this over here. And now what we like to do is we like to pretend that we're almost multiplying these d's by each other and multiplying these dx's by each other to write d squared y over dx squared. Now to be clear, this notation is a little bit misleading because we didn't actually perform any multiplications here. We just applied the operator twice. But it is a handy notation because it's a little bit shorter to write than this over here. I hope you recall that there's actually one more way that we can write the derivative of f of x. We said that we could also take f of x and then put a dash over here to write the first derivative. Well, to make this into a second derivative, all we really need to do is to just add another dash. That's another way to write the second derivative. Now there is also one more notation that you might see in the wild, and that's to replace this double dash with the number 2 with brackets. Some people even write this without even adding on these brackets, but most of the time you do see it with brackets. But this notation isn't really so popular, so I'm going to remove it from the list. You should just be aware of the fact that it does exist. Okay, so I don't usually start with a notation, but the reason I did this time is because the notation is really suggestive of exactly what the second derivative does. To demonstrate this, I'm going to go ahead and start off by drawing the function machine for the function f. Now I want you to remember that f takes in some number x and returns a new number which we call y. Now, as you already know, in order to turn this function f into its derivative, we need to put it through the differentiation operator. So let me draw it onto the page now. Okay, so as you saw, when you took this function f and put it through the differentiation operator, what we got out the other side was this new function f dash. This function f dash, when given the same input x, doesn't actually return a y value, but instead it returns the slope at that y value. Okay, so far I should just be repeating what you already know. But we said we wanted the second derivative. So in order to get that, we should actually put this function f dash through the exact same differentiation operator one more time. Okay, so in principle, this new function that we have here, f double dash, takes the same input x, but instead of producing the slope this time, it actually produces the slope of the slope, whatever that means. Okay, so to actually help you understand what d squared y on d squared x actually geometrically represents, I'm going to start with the graph of some random function f of x. Okay, so in order to actually properly understand the second derivative, it might help to have a graph of what it would look like for this particular function. Now, we already know how to draw the first derivative, so let me go ahead and start by actually just drawing on an axis. Okay, so when I showed you how to actually graph the derivative, I said that the first thing we should do is to actually find all the points where the maximums and the minimums occur and mark them on the graph below. Okay, and then the next thing to do is to actually look at the slope right at the beginning and mark it on the graph below. Since we're starting negative, we're going to mark it down here, and then we're just going to follow the graph all the way through until we get to the end. Okay, but there's just one point that I want to point your attention to. Notice that at this point right here, the gradient seems positive, but then instead of going back down, it just goes right back up. And that's reflected in the derivative graph down here. Okay, now that you have this first derivative graph over here, we said that the second derivative is just the derivative of this derivative. So we should go ahead and draw that by starting with an axis. Okay, so the first thing we're going to need to do to actually draw the second derivative is to, again, mark the maximums and minimums on this graph, and then copy them down here. Okay, and then just like before, we need to look at the slope right at the beginning. We can see that it's positive, so we're going to start up here and then follow the graph all the way through to the end, just like we did before. Okay, so this curve right here is actually the second derivative of this curve up here. But the real question is, how is this curve related to this curve right up here? To help you see this a little bit better, let me go ahead and actually extend these dotted lines all the way up to the top function so we can see what they signify. To make sense of this, let's just pick a few points and see how their second derivative behaves. Let's start with this point right over here. Notice that its first derivative is exactly equal to 0, and if you follow this all the way down, we can see that its second derivative is negative. If you look at the function carefully at that point, it sort of looks like we're going over a hill. If we look at this point, however, we know that its first derivative is also 0, but if we look at its second derivative this time, it's actually a really positive number. So the value over here kind of corresponds to a positive second derivative. And finally, if you pick some point where the second derivative actually equals 0, and you follow it all the way up, it looks almost like we're transitioning from a hill to a valley at that point. And if you think of this for long enough, I think you'll come to the exact same conclusion that I came to. If this function over here represents the height of the graph at any given point, and then this function over here, which we call the derivative, represents the slope of the graph at any given point, then this function over here is actually going to represent the rate at which the slope of this function is actually changing. Okay, so let me repeat this one more time. The second derivative measures the rate at which the slope of your function is actually changing. But just saying that doesn't really help you visualize what's going on at all. So what I'm going to do is I'm going to start off with some random slope. And then I'm going to make 3 copies of this slope to just show you exactly what's going on. Okay, so let me start with this function over here. I want you to imagine that we have some skateboarder right at the beginning of the ramp. Okay, so the second derivative measures how the slope is changing at this point. So if our second derivative is 0 at this point, doesn't that mean that the slope of the skateboarder is not changing as they move across the hill? Now, of course, the second derivative is only measured at a point. So at this point, we're saying that the slope doesn't actually change. So the skateboarder will keep moving in a straight line. Of course, this doesn't really tell us what the skateboarder is going to do later. They could go off and then start doing any curve that they like. But in this particular case, we're going to assume that the second derivative stays 0 the whole way. And that means the skateboarder is going to go off on a completely straight line. Okay, so I want to turn our attention to this slope on the right over here. And I want to imagine that we have a skateboarder at the bottom of the ramp again. By using this skateboarder, we're going to investigate a positive second derivative. I want you to imagine that the skateboard is moving, but then they start turning upwards as they move. So instead of the graph going straight and following the direction of the tangent over here, the graph decided to go upwards instead. And that's exactly what a positive second derivative implies. Another way to visualize positive second derivatives is to imagine your function curling counterclockwise. And as you know, a counterclockwise direction is also the direction of a positive angle. Okay, then the last thing to do is to investigate what a negative second derivative would look like. I'm going to do that by drawing the exact same skateboarder on this graph. Okay, so this time, as the skateboarder moves forward, instead of dipping up, they're going to dip down instead. Again, the fact that the graph hasn't actually followed the tangent, but instead decided to go below it, indicates that your second derivative is actually negative. Again, if you imagine this like a piece of paper, you can imagine that the piece of paper is curling clockwise this time. And a clockwise angle, as you know, is the same thing as a negative angle. And if you look carefully, this is the exact same behavior we see on the graphs. Notice that this part looks like it's curling down, and as we saw, this led to a negative second derivative. Then notice that this part is curling up, and that led to a positive second derivative. And this part over here looks really straight, and if you follow it down, surely enough, you notice that its second derivative is exactly 0. Now initially, all 3 of these functions are increasing, because remember it's the first derivative that tells you whether you're increasing or decreasing at this point. But the second derivative measures whether or not the rate at which you're increasing is changing. So for example, in this case, we're increasing but at a decreasing rate. Now similarly, for this function over here, we are increasing, but we're doing so at a constant rate. And now finally, in this case over here, we're also increasing, but this time we're increasing at an increasing rate. Okay, so now I hope you have a pretty good visual intuition for what the second derivative actually gives you. But I'd like to give you some examples to show you why we'd want to use it and exactly where it would be useful. Okay, but before I actually go ahead and show you the example, I'm going to stop here for now because this lesson's getting a little bit long. So tune in to the next part where I'll actually show you exactly why you'd want to use these second derivatives and exactly why they're useful.